All right, got that going. Okay, so today we are going over Newton's laws of motion. We're basically going over the postulates now for the majority of what we'll be doing in the rest of this book for classical mechanics. So up till now we've been doing what we call kinematics. Kinematics is where you study how an object moves, given information about how it moves already. So given its position, initial velocity, and acceleration, find where it will be in 10 seconds. That's a kinematics question. Now we're moving into a field called dynamics. Dynamics is where you know what's causing the change in the system. So in kinematics, you just knew that there was an acceleration. You just knew this marker was accelerating downwards. In dynamics, we say, why was it accelerating downwards? Force of gravity.
Yeah.
So we introduce forces into the picture now. So I say, here's the force pushing this object. Now calculate its acceleration. You see a difference? So rather than telling you already how the object's moving, I'm going to tell you the forces being applied to objects, and now you have to describe their motion from those forces. So that's dynamics. So kinematics is nice because it helps you get comfortable with a bunch of just definitions and working with definitions. And now dynamics, we're getting into the foundations of classical mechanics. So that's what we're going to be focusing on today, the foundations of classical mechanics. We're going to be focusing on forces. Forces are what are responsible for everything that is interesting in the universe to happen in the universe. You're very used to working with forces. There's 4 forces. There's gravity, and you're very familiar with gravity. That's one of the things that causes things to happen in the universe. The next one that you're very familiar with, even though you might not think it, is the electromagnetic force. This is a force that you use with the majority of forces. Basically, anytime you experience a force or see a force occur, see the consequences of a force, it's the electromagnetic force if it wasn't gravity. When I throw this marker and it hits this and it stops and it collides, why did it stop and collide? That's the electromagnetic force. If I were to break this down and look at this marker has atoms. Here's the nucleus of the atom, and around it, there's electrons going around it. And the whiteboard has atoms, and around it are electrons, and 2 electrons repel each other. And so this won't go through the whiteboard. It's a very strong force. The closer you get, the stronger it is. So every time you punch someone or someone punched you, every time you step on the floor and don't fall through the floor, every time you push a button, that's all the electromagnetic force. Not to mention the force responsible for actual electricity, the way that you probably think about the electromagnetic force when you hear it. Yeah. And then the other 2 forces are called the weak nuclear force and the strong nuclear force. The weak nuclear force is responsible for making atoms decay, basically. So you hardly ever come across that, but that's why I like used uranium after it comes out of a plant. You hear it's radioactive. That's because the weak nuclear force is very active in it, causing it to decay. And then the strong nuclear force is what holds atoms together. You might have learned that inside the nucleus of an atom, there's these things called protons, right?
Yeah.
And protons are positively charged. And inside the nucleus of an atom, you have 2 protons right next to each other. How does that work? Shouldn't they be pushing each other apart very, very hard?
Except they're positive.
Yeah. Like charges repel. Opposite charges attract.
Oh, yeah.
So why are these protons just shooting apart? And the answer is the strong nuclear force. So the strong nuclear force is a very, very, very strong force, but it only interacts over very, very, very small distances. So when I get them really close together, the strong nuclear force is able to interact, but then if I have them further apart, now they'll just shoot apart due to the electromagnetic force. Okay, so those are roughly the 4 forces. But force is what's responsible for all change, everything interesting in the universe has to do with forces. Okay, so some types of forces that you'll be working with commonly in this book. First off, there's contact forces. Contact forces, that's just due to actually making contact with an object to apply a force. When I slide a box, I'm applying a contact force. The normal force. It's called normal because it's always normal to the surface it's on. So if I take a box, if I have a ramp and I stick a box on that ramp and that box isn't sliding, I know that I have gravity pulling the box down, right?
Yeah.
But I also have a normal force, which is always pushing that way. You are experiencing a normal force on your chair right now, pushing up on you. Gravity is pulling you down, the normal force is pushing you up. If there was no force pushing you up and gravity was just pulling you down, you'd be going down, but you're not. If I pulled that thing out from under you, there's no more normal force, you fall.
Okay.
So the normal force is the pushback, and the reason we call it the normal force is it's always perpendicular or normal to the surface you're on. Make sense?
Yeah.
Okay, now friction. What's friction? If I have a box right here and I start pushing the box, or say like a refrigerator, something heavy, if I push it a little bit, the fridge doesn't slide. I have to push really, really hard, and I have to overcome the force of friction. So friction is a force that's is resistive to objects sliding across each other. Why doesn't the fridge slide when I start pushing? I'm applying a force, how come it's just staying there?
Because it's stuck on the ground.
Because it's stuck on the ground, but what does that mean? What does that mean it's stuck on the ground? Because if I push a little bit harder, it's no longer stuck on the ground. It's not like I picked it up. It's still on the ground. How come there's some amount of force that allows me to start sliding that thing? So we're overcoming the force of friction. So even in this scenario, imagine that this box here on this ramp still isn't sliding. So let's imagine that's a scenario for a second. Well, notice gravity is trying to make it slide down the ramp, right?
Yeah.
It's not sliding down the ramp, which means it must be experiencing some force of friction in the opposite direction. Friction always opposes the way you're trying to push it. If I'm trying to push a fridge, if we have a fridge right here, and I'm applying a force this way onto the fridge, trying to slide it, there must be a force of friction pushing this way, stopping it from moving, if the fridge isn't sliding.
Yeah.
Same thing with the box. If the box isn't sliding down the hill, there's definitely some force trying to pull down the hill, right? Gravity's trying to make it slide. If it's not sliding, there must be some friction holding it there. And so this vector plus this vector must equal this vector. They perfectly cancel each other out. They're the negative of this. So if I were to add these two vectors together, that would give me one that looked like this, that perfectly cancels out this vector. So the net force on it is 0, because it's just staying there. If the net force wasn't just 0, it wouldn't just stay there.
Okay.
Okay, friction, tension. What's the force of tension? The force of tension is the force inside of a rope when we're pulling on something. So now I've got the fridge and I've got some rope wrapped around the fridge, and I'm over here and I'm pulling on the rope. Now there's a force of tension in the rope pulling it that way. Right?
Yeah.
Similarly, there's tension in the rope on my end pulling that way. I feel a force that way when I'm pulling on it, and the fridge feels a force that way from me pulling on it. Right? If there were a rope between you and me, and I pull on that rope, I feel a pull back that way, that's tension, but you also feel a pull this way, that's tension. Weight, that one's pretty intuitive. You stand on the ground, there's a force downwards, that's your weight.
How's that different from gravity?
Weight versus gravity. We'll jump ahead a little bit. Here's the Earth, since I can't think of a better one right off the top of my head to explain it. And here's a space station. Give you some quick intuition for orbit, so that this will make sense. On the Earth, imagine I throw a ball. And let's say I throw it absurdly well, just absurdly hard. It might follow a path something like that, right?
Yeah.
Well, I throw it even harder, it might follow a path something like that, right? Well, what happens if I throw it so hard that it falls at the same rate that it goes around the Earth? That's what we call orbit. Okay?
Okay.
So imagine for a second now you're in orbit. You're experiencing gravity. Gravity keeps pulling you down. But if you were in the space station, you'd also be weightless. So while gravity causes you to have weight, just because there's gravity doesn't mean you have weight. And you can be weightless.
Okay.
Make sense?
Yeah.
Okay. So they're definitely closely related. Without gravity, there's no weight. But just because there's no weight doesn't mean there's no gravity. But weight, what you know and love, it's the force you're exerting down onto the ground or whatever you're standing on. And then finally, there's what we call long-range forces. And a long-range force is one where there doesn't need to be any contact. This is like gravity. Gravity is a long-range force. This marker isn't touching the ground, and yet it still falls to the ground. Notice with these, there had to be some sort of contact going on. Long-range forces, there doesn't need to be any contact. Make sense?
So if it was something like air resistance, is that friction or?
Air resistance would be like friction. Yep. So friction, we just put friction here. We have special names for different types of resistive forces, but basically forces that are resistive to motion. So yeah.
Okay.
Very simple. And this isn't a complete classification. This is just meant to give you intuition to a bunch of different types of forces. So like you have intuition for what we're going to talk about now, because now we're going to talk about forces.
So the force of gravity on that, this would be on weight?
The force of gravity causes you to have a weight force.
Is it a different kind of force than these forces? Or
Is
how
gravity?
isn't on here?
Gravity is a long-range force. But remember, this isn't exhaustive.
Yeah.
It's just trying to give you intuition for what forces are, so now we're going to talk about forces.
Okay.
Good? Okay, so now before we get to Newton's three laws, we need to introduce one more concept, which is like technically a postulate, but it's not one that Newton explicitly stated. But it's a base assumption that we make about forces. In short, the assumption is that we can treat forces like vectors. There's no proof of this. This isn't something that we prove. We didn't start at some simpler concept and prove that you can model forces with vectors. It's an assumption based off of experimental data. So what in particularly that means is we can add up forces the same way we add up vectors. It means that if I have some box and I've got some force pulling it this way with a magnitude of 10 newtons, that's just our units for force, and I have another force this way pulling on it this way with 10 newtons, and I have a force pulling straight up with 2 newtons, add all those together, and the net force is just pulling up on it with 2 newtons. So it's called the law of superposition, so it's one of our assumptions basically, or the principle of superposition, something like that. Superposition principle. So it's one of our 4 basic assumptions about classical mechanics. Is forces can be modeled with vectors, and particularly you can take the superposition of a bunch of vectors, basically do a vector sum of a bunch of vectors, and the resultant vector behaves the exact same way as all the individual vectors.
Yeah.
Make sense? Now, I happen to make a scenario where that vector was the same as that vector, but that's not what I mean. This is just a sum of all these 3. It's coincidence that the sum of all these 3 happen to be one of those vectors.
So it could be like on an angle or something?
Yeah, so if I would have just done that, that's equivalent to a force of magnitude 0 pulling on this. Or if I would have made this 11, that's equivalent to a force of 1 Newton pulling that way. Add them all together, do the vector sum of all these, and it gives you that vector.
Okay.
So one of our 4 basic assumptions, but not one of Newton's laws. So, because obviously Newton was, well, he was the second one to do it, really, but. Anyways, now we'll jump into Newton's 3 laws. Newton's first law, which was actually first stated by Galileo, it's called the law of inertia. And what this law states is that the way it's typically summarized is an object at rest remains at rest unless acted upon by force, and an object in motion remains in motion unless acted upon by a force. Let's see how the book phrases it exactly. A body acted on by no net force moves with constant velocity, which may be 0, and 0 acceleration.
What?
A body acted on, okay, so maybe this one's worth writing. So our first law. A body acted on by no net force Net force meaning when you add up all the forces acting on, that object, they add up to a zero vector.
Okay.
So that's what we mean by no net force. By no net force, so a body acted on by no net force moves with constant velocity. So think about this marker out in space for a second.
Okay.
So you are out in space with just this marker. Now imagine you give the marker, well, first off, the marker is just sitting there not moving relative to you. Is it ever going to start moving relative to you? Not if you don't apply force, right?
Yeah.
So as long as you don't apply a force, that body, since it's not being acted on by any net force, moves with a constant velocity, namely zero.
Okay.
Now imagine you give it a little push. So now it's moving over 1 meter per second. It's going to continue moving by 1 meter per second forever unless another force is applied. So that body acted on by no net force moves with constant velocity until some other force comes along. But if it's no net force, then it doesn't change. Here's another example. Look at this book. It's sitting there. And it's just going to sit there and not move until some net force acts on it. Now, force is acting on this book. If we draw the book, here's a book, and it's on some table. It has its weight down, and it also has a normal force pushing up on it. So gravity's pulling it down. Normal force of this is pushing it up. They're pushing the exact same hard, and so the book's just sitting there. So no net force is acting on the book. The net force on the book is zero. But then I can come and apply a side force, and now it moves, and it accelerated just barely.
Yeah. When you draw the table's forces, do you include the books downward?
You can treat the book and the table all together as one point object. The same way that I don't draw something separate when I do forces on you, I wouldn't draw one for your body and one for your head. I could treat them separately and I could treat them the same. Depends on where the force is being applied. If I'm applying a force right here, it doesn't really make sense to treat them differently. The book is just like adding to its weight.
Yeah.
If I'm pushing right here, now it makes sense to treat them differently. So it just is a matter of what makes sense for your problem.
Okay.
I mean, there's going to be some problems where you treat the whole Earth as a point mass. So that's contextual. But as long as there's no net force acting on an object, it moves with constant velocity. And remember, velocity is relative. Do we want to have that discussion again? Velocity is relative, meaning let's assume that you and I are now floating in space.
Okay.
Except for me and the marker relative to you are moving like this together. From my perspective, you're slowly floating that way. From your perspective, me and the marker are slowly floating this way. Who's right, who's wrong? I say that marker's holding still. You say, no, it's moving that way at 1 meter per second. Who's right?
Neither, it's just perspective.
It's relative. So velocities are relative. So if it is moving with constant velocity, then in some reference frame, it's actually holding still. It takes net forces to change that. Now if we apply force, now there's a difference that both you and I can talk about. So if the net force is zero, then it moves with constant velocity. Now, I don't really like the way this book says it, because they should say, his first law is that there is a reference frame such that this is true.
Okay.
There exists some reference frame you can be in, such that in that reference frame, if the net force acting on a body is zero, that body does not accelerate. Okay, so now we have our definition for what we call then an inertial reference frame. An inertial reference frame is a frame of reference. A frame of reference where law 1 holds. So if in your reference frame, when it looks like there's no net forces acting on an object, its velocity is constant, you're in what we call an inertial reference frame.
What do you have to be an inertial reference frame?
So let's give you an example of not an inertial reference frame, really quick. So let's say really quick that we've got a glass bus, and I'm inside the glass bus, and I'm on rollerblades. Let's put me close to the front. So I'm inside the glass bus on rollerblades that are perfectly frictionless.
Yeah.
So perfect friction. And then Peter, he's duct taped to the front of the bus, looking back at me. So he's going to move in the frame of the reference of the bus.
Yeah.
And then you're standing out here watching both of us. Okay? So you're both watching me. We're on the bus. The bus starts accelerating forward. When the bus starts accelerating forward, what happens to me?
You get pulled back.
I get pulled back. I suddenly start moving back. Right?
Mm-hmm.
So from your reference frame, I actually just hold still and the bus moves forward. So in your reference frame, I don't move. I stay here and the bus moves forward until I hit the back of the bus and it hauls me along. That makes sense? But in Peter's reference frame, notice what happens to me. I magically start moving backwards. And there was no forces being applied to me.
Yeah.
His reference frame is not an inertial reference frame. The intuition is, if your reference frame is accelerating, it's not an inertial reference frame. And the laws of physics that we're going to derive only hold in inertial reference frames. So from Peter's reference frame, there's suddenly a magical force. From your reference frame, everything makes perfect sense, and the laws of physics hold. Peter's reference frame is not inertial, yours is. An inertial reference frame. Almost every problem that we deal with in this book, we're going to assume that you're in an inertial reference frame. It's the reference frame in which the laws of physics hold. Does that make sense, the difference?
Yeah.
Okay. So, first law says, there exists a reference frame where the net force acting on a body produces a constant velocity. We define such a reference frame to be an inertial reference frame. Good?
Mm-hmm.
Second law. Second law says F equals ma. The force on an object is equal to, the net force on an object, this is the net force, is equal to an object's mass times an object's acceleration. Let's get a quick demo of that. Imagine I've got some box here, and it's on a sheet of ice, perfectly frictionless. And let's say that this box weighs 10 kilograms. You with me?
Yeah.
Now say you are on the ice, and you push this box now, and you give it a push this way. You're pushing it this way with 10 newtons. How much does a box accelerate?
I don't know how much newton is.
Doesn't matter. We know that you're pushing with 10 newtons is equal to the mass of the box, 10 times its acceleration.
So it's not accelerating one.
So it has an acceleration of 1 meter per second squared. 1 newton, just give you the units. A newton is equal to a kilogram, what if I put a dot there? 1 newton is equal to 1 kilogram times meter per second squared. That whole thing we call newton. Notice, mass is kilograms, acceleration is meters per second squared, so force is kilogram meters per second squared.
Okay.
So that's what 1 newton is. But anyways, so yeah, as long as you are pushing on that box with 10 newtons, it's going to accelerate at 1 meter per second squared. Go ahead.
Hi.
Hi. I'm actually looking for Jaslyn Williams.
She's up in room 5.
She's in room 5. Oh,
I
thank you.
believe.
Okay, appreciate it. Good to see you.
See you. Okay. So as long as you're pushing this box, it's going to accelerate 1 meter per second squared. If you push this box for 3 seconds at 10 newtons each time, after 3 seconds, it's going to have an acceleration of 3 meters per second squared.
Yeah.
Good? If you can keep it up, yeah. No, I don't think I'm saying that right. Sorry, I said that wrong. Let's not think about continually applying force. We'll just say one force at one moment. You push it hard with 10 newtons, it's now accelerating at 1 meter per second squared. Let's leave it at that for now.
Is there anything that's going to stop that?
Box from sliding?
Yeah.
Not if this ice is perfectly frictionless. Really, ice has a little bit of friction.
Yeah.
And so really, it's going to slow down over time. Because really, you're going to have 10 newtons pushing that way. Let's say that friction is causing a pushback of 1 newton. That means friction is actually causing you to de-accelerate by 0.1 meter per second squared.
Yeah.
So you'll apply some acceleration and it will slow down, slow down, slow down, slow down, and stop.
Mm-hmm.
We'll get into friction in the next section. Anyways, so F equals ma. Probably the most important law in all physics. F equals ma. And notice that your acceleration vector and your force vector point in the same direction, which makes intuitive sense.
In the same direction?
Yes. This vector is equal to this vector scaled up by mass.
Okay.
So they point in the same direction, they just have different scales. And the bigger the mass, the smaller the acceleration for the same force.
So every time you're plotting a force and acceleration, it's just going to be the exact same direction, just different sizes.
The net force.
The net force.
Yeah, you need to add up all the forces on an object. Whichever way that force vector points, that's the way the object will accelerate. How fast will it accelerate depends on the mass. If it has a teeny mass, it will accelerate a lot. If it has a really, really big mass, it will accelerate a little.
Why?
Well, just think about the numbers for a second. So let's say you apply a force of 100 newtons, right?
Yeah.
If the mass is 100, what's the acceleration?
1.
If the mass is 1, what's the acceleration?
100.
There you go.
Okay.
So, Newton's second law. Now, Newton's third law. Third law is the one that's often summarized as for every action there's an equal and opposite reaction. And it says that the force from A on B, so we'll do A comma B, that force is equal to the negative of the force from B on A. Let's make sense of this one for a sec. Imagine I have a box here, and I have a box here. 2 boxes.
Okay.
You're over here, and you push the boxes. We'll call this box A, we'll call this box B. A is going to push on box B.
Yeah.
And we call that the force of A on B. B then pushes back with the exact same force, but in the opposite direction.
Okay.
Make sense?
Yeah.
Think about if B pushed back with less of a force. Then what would happen? You're pushing on A, B might accelerate away.
Oh.
You're pushing on box A and box B just starts taking off. That doesn't make sense.
Mm-hmm.
And then if it pushed back with a smaller force, then you push A and it starts like going through box B or something.
What about something like little pendulums, where it hits one side and the other side goes?
That's transferring momentum, and that will be like chapter 7 or 8, I don't know. But we'll get to that exact thing. But this isn't that. This is just forces. So for every action, there's an equal and opposite reaction. Here I am pushing on the floor. With my weight, the floor is pushing back on me with the exact same weight. The force I apply to the floor also applies right back to me. If it didn't, if it applied more of a force, I'd for some reason be shooting up in the air. If it applied less of a force, I'd be falling through the floor. But I'm not moving. So my net force must be 0.
Then how does anything move?
So, let's put some numbers in here really quick.
Okay.
So let's say that we've got a box of, I don't know, we'll keep the number small, really small, 1 kilogram. Say 10, be a little bit more realistic. So we got a box of 10 kilograms and we got a box of 20 kilograms. And they're on a perfectly smooth, frictionless surface. We're ignoring friction for now, right? And let's say that you come along and you push this whole thing with a force of, I don't know, we'll say 20 newtons. You good so far? So let's look at the force that you exert on this box.
Okay.
So from this box perspective, well, first off, let's think about the whole system and how the whole system accelerates. Maybe that will be the easiest thing. We'll call this box A still, and we'll call this box B still. So first off, we know that force is equal to mass. The mass of both the boxes is 30 times acceleration.
Yeah.
And so, that gives us that A is equal to, well, I'll just say m sub A plus m sub B. So the sum of the masses times the acceleration is the net force, which gives me that the acceleration of the whole system is equal to force divided by the sum of the masses.
Yeah.
So let's just make the force 30 newtons just so that all the numbers come out really clean. So if the force was 30 newtons, then the acceleration is going to be 1 meter per second squared, right?
Yeah.
So that's how the whole system accelerates. Good?
Mm-hmm.
Okay, so now let's think about just one of these boxes. This box here. So what is the force then that box A exerts onto should we be jumping this far ahead? I'm kind of thinking, now that I've explained all the new material, I should just, we can keep going with it. Yeah, let's stick with it for a second. Okay, so the whole system is accelerating that way. Now, the force that A exerts on B then, well, we'll just say the magnitude of force. We know the direction. The direction's that way, so we'll just keep it simple. So the force that A exerts on B is going to make this accelerate at 1 meter per second.
Yeah.
So, if that's accelerating at 1 meter per second and it's 20 kilograms, then I know that the force of A on B has to be 20 newtons.
Mm-hmm.
Okay, now let's see. We know the net force on A. What's the net force on A?
30.
Not the net. That's what this is. This is 30 newtons. Well, we'll just calculate for a second now. So if F from A to B is 20 newtons, then F from B to A, according to that law, has to be minus 20 newtons, right?
Yeah.
So the net force on just object A then is equal to what? Look, two forces acting on this. I'm pushing it that way. This box is pushing it that way. How hard am I pushing it that way?
30 newtons.
How hard is it pushing that way?
Minus 20 newtons.
Yeah, so minus 20 newtons, or it's pushing 20 newtons that way, right? 20 newtons in the other direction. So the net force on the box then is 10 newtons. So now if I push on a 10 kilogram box with 10 newtons, what should its acceleration be?
Just 1.
1, which is exactly what we calculate for both boxes,
Okay.
right? So this one gets 20 of the newtons. This one this one box only has 20 newtons pushing on it. From that box there. This box has 30 pushing on it this way and 10 pushing on it that way. Or 20 pushing on it that way. And so the whole system moves. Even though at the contact of these two boxes, there's 20 this way and 20 that way.
Yeah.
Make sense? Okay. And the fact that for every reaction there's an equal and opposite reaction, this is also the base idea behind a balloon. I blow up a balloon. And I let it go. What happens?
It'll just fly.
It flies. What happens? It pushes out the air that way, and the air pushes back on the balloon that way,
What about
causing the balloon to go. It's actually how a rocket works. What do we do inside of a rocket? A rocket has a big fuel tank. It shoots out its fuel that way very, very, very fast. And so the fuel has to push back on the rocket, causing the rocket to go up and the fuel to go down. Good?
what would be an opposite force on friction?
So, when I push the fridge, so let's say that there's friction now. So here's some box, doesn't really matter its weight this time. Let's say I'm over here and I push the box, and I'm pushing it this way with 20 newtons. And it's not sliding.
Okay.
That means that the box has to have a force of friction pushing this way with 20 newtons. And so the box pushes on me with 20 newtons, and I push on the box with 20 newtons, and nothing happens. All right, now I'm pushing the whiteboard with 10 newtons, and it's pushing me with 10 newtons. And none of us are moving, because the net force is 0.
Okay.
Net force is 0 because there's also friction between the ground and me. So friction's pushing me that way with 10 newtons. The wall's pushing me that way with 10 newtons. I'm not moving. I'm pushing the wall that way with 10 newtons, and we'll call it friction, I guess. It's stopping the wall from moving this way with 10 newtons. And so the wall stays there. And we'd have to overcome a lot of force to get the wall moving.
Okay.
Okay, so those are fundamentally our 3 assumptions. Well, 4 of them. 1, we can treat vectors, or we can treat forces like vectors. 2, if there's no net force, it's not moving. We call that an inertial reference frame, which are the frames of reference that we're interested in. F is equal to ma. This is how you calculate how it will move given some net force.
Yeah.
And then for every reaction, there's an equal and opposite reaction. So as far as new material, I think that's almost it. They have one more conversation about weight and mass versus weight. So weight is a force. Weight is a force that you apply on the ground. How do I calculate how much weight then you apply on the ground? So what is your weight? Your weight is equal to your mass times your acceleration downward, which is g. G, 9.8 meters per second squared, assuming you're close to the Earth.
Okay.
So this is your weight. It's your mass times your acceleration gives you your weight. When you step on a scale, that's a force,
Yeah.
right? And it's measuring your weight. Weight is a force. So pounds, the way that you measure pounds going on your scale, that's using the, what's the other system called? Not the metric system. So we use newtons, we don't use pounds. We don't use this, we use newtons.
So
The same way we use meters, we don't use feet. So pounds measures the same thing that newtons measures.
then was kilograms.
Yes, exactly. This is one of the most terrible things that we do in our system. We convert from kilograms back and forth between pounds, which makes no sense. They are fundamentally different units. Kilograms is a measure of mass, pounds is a measure of force. When you get your weight in kilograms, when they give you your weight in kilograms, what they really mean is if you take that amount of kilograms, multiply it by 9.8, and then convert that to pounds, then that's how they convert it to pounds. But this is a measure of mass. It is not a measure of weight. Newton is a measure of weight. And I have no clue how this started. How we went from pounds to newtons, or pounds to kilograms as our conversion, rather than pounds to newtons. But for some reason, that's the way that it is. So kilograms, that's a measure of your mass. Pounds, that's a measure of your force, of your weight, the force you exert downwards.
How do you measure mass?
How do you measure mass? Here's one way you can do it. What's your mass? Take your weight divided by g, gives you your mass. But first let's get intuition for what mass is. How would you describe what mass is? Because it's not just your weight. I could throw you out in the middle of space. Okay, now you have no weight. What's your mass? Is it still the same?
It's your matter.
Yes, it's your matter. We can think about mass somehow approximates like all the electrons, protons, and neutrons that go to making you up. And that's what your mass is. It's like a count of how much matter goes into making you up. Right? That's one way you can think about it. Another way to think about mass is it's your resistance to change direction, change motion. The more mass you have, the harder it is to accelerate you.
Okay.
It's your resistance to change motion. That's another way we can think about it. And so even if we were in outer space, we could still measure your mass even though you don't have a weight. And we would use springs to do that. We could use something called Hooke's law. The way that works is roughly like this. We'll get a lot more detail into this later because Hooke's law is a big deal. Probably in the next chapter, I don't know. So imagine let me draw that a bit more compact. Imagine I've got some spring here. You with me?
Okay.
And I stretch it out. So here's where it naturally is, x equal to 0. Here's where it naturally wants to be. And I stretch it out some distance, and I attach a mass next to it, m that I don't know. You with me?
Yeah.
So when stretching the string causes there to be a force this way on it. You with me?
Mm-hmm.
And so anytime I pull out a spring this far, there's the same force this way. And so we'll call that m1 really quick. And so that force, whatever that force is going to be equal to m1 times how much it makes that thing accelerate. And we can measure the acceleration. You with me?
Yeah.
And then I go and I get some mass, that I define to be exactly 1 kilogram. Because 1 kilogram, that's a physical thing. There's some arbitrary piece of platinum in Paris somewhere that we said, this is 1 kilogram, by definition. So whatever that thing is, remember, all our units reference something physical in space that you can go grab. So then go get that reference material, whatever that is, 1 kilogram, and you stick that on there. And you stretch out the same way. It's going to be the same force that the spring pulls back on, right? The force doesn't know if you attached a heavy weight to the end of it or a light weight to the end of it. It's going to pull back with the same force, no matter what. It's going to recoil with the same force.
Okay.
Does that make sense? And so it's just going to be a different acceleration. So I know that F is also equal to 1 kilogram times the acceleration that you measure when that goes back. You with me?
Yeah.
Since these are the same forces, I now know M1 is equal to A2 divided by A1. And now I have M1 in terms of our mysterious mass in terms of
Acceleration.
as a ratio of those two accelerations. Yeah. See how I did that?
I think it's...
Let's just make sure it's very explicit. Same force, same force. So M1 times A1 is equal to 1 times A1, which is just A2. So M1 is equal to A2 over A1. And that's how you measure its mass, even out in space. Mass is a property you have everywhere. It's no way dependent on gravity. Weight is 100% dependent on gravity. No gravity, no weight. But no gravity, that doesn't change your mass. Your mass is your mass. Make sense?
So when you let go of the spring, isn't that affected by like gravity, friction, and tension as well?
Oh, sorry. Let's say that the spring, this object is sliding on a perfectly smooth surface.
Okay.
Sorry. Yeah, it's kind of implied when you write horizontal springs, but it's only implied after you've seen a few problems with it. Yeah, otherwise you're thinking, why isn't it just falling? Yeah, sorry. My bad. Yeah, so frictionless smooth surface, so it's just moving this way. Now does everything I said make sense?
Yeah.
And if you think about out in outer space where there's no gravity, then we don't need the frictionless smooth surface. Right?
Okay.
So even in outer space, mass makes sense, and you can measure your mass. It doesn't make sense to talk about your weight in outer space. Your weight is dependent on gravity, and that's why they say things like, you weigh more on the Earth than you do on the Moon. You don't have more mass on the Earth than you have on the Moon. You weigh more. So weight is your mass times the acceleration due to gravity. mg. So that's typically how we'll represent. Weight is just m times g. And then we'll typically draw that in the down direction, so that you don't need to put a unit sign in there. It's going to be a downward vector.
Yeah.
Okay, so that's weight. So now with all that, we'll just start. We'll go back to the beginning and just turn through the example problems. Example. 3 professional wrestlers are fighting over a championship belt, shown in whatever figure. The forces have magnitudes that find the x and y components of the net force on the belt. Okay, so they're relying heavily on a picture here. 4.8a. I hate that they do this. Okay, we don't need this anymore. We'll just start solving problems. So we got the belt right here. Here's our coordinate system. We draw our coordinate system centered in the belt. Doesn't matter how we do it, but there we go. We have one wrestler is pulling this way. We call that F2. We have one wrestler is pulling down, F1, and we have one wrestler is pulling on an angle of 53 degrees. This was F3. And one wrestler is pulling on an angle of 53 degrees. Here's F1. And this is 53 degrees. Okay, and they give us the magnitudes of the vectors. We know that F1 is equal to 250 newtons. 250 newtons. F2 is equal to 50 newtons. And F3 is equal to 120 newtons. So our job is to find the net force of all 3 of these. And typically, the way we break this up is we calculate the net force in the x direction and the net force in the y direction.
Okay.
Make sense? So when we use subscripts, when I use subscripts for the forces here, then capital F by itself means the net force.
Don't they have different net forces?
The net force on the belt, so they're all pulling on this belt, right? One's pulling that way, one's pulling that way, one's pulling that way. This is like a bird's eye view.
Yeah.
The net force is the sum of all the forces. Which way is the belt going to move now?
Okay.
That's what we're trying to figure out. You with me?
Yeah.
And so I'm saying, I'm going to use now F, just F by itself, to talk about the net force. This is F1, this is F2, this is F3. F now is the sum of all the forces. And that's just going to be a convention I follow.
Mm-hmm.
Okay, so let's split this up into the x direction and y direction. Obviously, this one's completely in the y direction, this one's completely in the x direction. I need to take F1 and split it up into its x component and its y component. So I need this force right here is going to be F1 in the x direction. And then this force right here is going to be F1 in the y direction, right?
Yeah.
And then if you redraw your forces in your diagram, it's common that you put like a squiggly through there saying, I re-accounted for this force somewhere else. So now it's like these 4 forces are acting on the belt. Same thing, right? So now in the x direction, so the x component of our net force is going to be equal to, we'll call that way positive and this way negative. So F2 is going to be positive then, and then this is going to be a negative 1.
Yeah.
So we'll have F2. What's F2?
50.
50. So we'll have 50 minus this one. This one is going to be 250 cosine of 53 degrees, right?
Yeah.
So that's f of x. We'll calculate whatever that is. So that's equal to my calculator. So let's see, we have 250 cosine of 53 degrees. And so, let's see how many significant figures I have here. I think they're assuming 2 significant figures. Anyway, this comes out to 100. So this comes out to minus 100 newtons. So Fx, in the x direction, it has a net force this way of 100 newtons, right?
Yeah.
And then Fy, we're going to have, again, I'll call this a positive direction. So we're going to have the magnitude of this minus the magnitude of this. So the magnitude of this one, that's obviously just what?
250 sine of 53.
Perfect. Minus F3 was 120.
Yeah.
So in the y direction, we have 250 sine of 53 degrees minus 120, which gives us 80. And that is going to be up.
Yeah.
So the net force vector, F, is going to be minus 100, minus 100 comma 80. I think they just want F sub x and F sub y. Just like don't get confused between me and the book. The book uses, for the total vector, they always use R. And they want you to think the resultant vector.
But it's the same thing as F.
But it's the same way I use F. And there's no way I'm going to remember to use R. You just get trained one way and that's how you do it.
Yeah.
So let's do another example problem now. In the classic 1950 science fiction film, Rocket Ship XM, that one's a classic.
Oh yeah.
A spaceship is moving in the vacuum of outer space, far from any star or planet, so there's no gravity, when its engine dies. As a result, the spaceship slows down and stops. What does Newton's first law say about this scene?
It's not gonna happen.
It's not going to happen. All right. What does Newton's first law say about the scene? It says that you're not in an inertial reference frame somehow. It says if this is real, then you're not in an inertial reference frame.
Yeah.
But if you are in an inertial reference frame, what's happening isn't real.
Yeah.
So we get that one.
Wow, that actually happens a bunch of movies.
Yeah, pretty stupid, huh?
It's a rookie mistake. This is why Star Wars is just the best.
No, the new Star Wars movies are super dumb.
The new ones are awful, but
Yeah.
the old ones are classics.
The old ones are classics. Okay, next. A worker applies a constant horizontal force with magnitude 20 newtons to a box with a mass of 40 kilograms resting on a level floor with negligible friction. What's the acceleration of the box? Well, we basically already done this one, but
Negligible friction is just zero friction.
yeah. So we're saying just ignore it for now since we're not to the next chapter yet.
Okay.
So here you are pushing on the box, and the box is 40 kilograms. So the box is 40 kilograms, and you're pushing the box. You're pushing it this way with 20 newtons. Oftentimes it's helpful to draw what we call a free body diagram. So a free body diagram is where you take the thing you're interested in, represent it as a point, in this case it's our box, and then draw all the forces acting on that box. So in this case we have a force this way due to the push of 20 newtons, and then we also have
Normal.
In the downward direction, we have mg, and in the upward direction, we have the normal force. Those two perfectly cancel out, so the net force is just that way. And that's called a free body diagram, so you don't make a mess of your picture. Because usually you want a picture to help you see what's going on, and then a free body diagram to help you just consider the forces. But, just so you're aware. Okay, so anyways, now we need to calculate the acceleration of the box. What's the acceleration of the box?
It's just half a newton, or half meters per second.
Perfect. A is just equal to 1/2 meter per second squared.
Second squared.
Yes, 0.05, I guess, two significant figures were given to us. Okay, next one. A waitress shoves a ketchup bottle with mass 0.45 kilograms to her right. I'm going to start writing down these numbers as I read, but I'll have to keep finding them. So, we have M is equal to 0.45 kilograms. Okay? She shoves it to her right along a smooth, level lunch counter. So I'm assuming no friction. The bottle leaves her hand at 2.8 meters per second. That's the initial velocity of the sliding. Then slows down. Okay, so there's going to be friction. Then slows down as it slides because of a constant horizontal friction exerted on it by the countertop. If it slides for 1 meter, so it moves 1 meter, delta x is 1 meter, or if we call x not 0, then x final is just 1. However you want to say that. What is the magnitude and direction of the friction force acting on the bottle? Okay, so we have the bottle here, and it slides over from 0 to 1 meters, and it's given an initial velocity of 2.8 meters per second. You with me?
Yeah.
And we know the mass of the thing. So what's our overall strategy? We're trying to figure out the force of friction, right? So while it's sliding that way, it has a force of friction pushing it this way. Force of, a little f of friction. Force of friction pushing it that way.
Okay.
The force of friction pushing it that way is going to cause a negative acceleration. So first we need to figure out what that negative acceleration is. Once we know what the acceleration is, since we have the mass, we can figure out the force of friction. You with me?
Yeah.
Now it said that it gave us that the force of friction, we know that the force of friction is equal to a constant, whatever it is. So it's not changing. Which means our acceleration isn't changing. Which means we can use our constant acceleration formulas.
Yeah.
That makes sense? Okay, so I know our delta x, I know our v naught, and I'm looking for our a. Well, I also know our final velocity. What's our final velocity?
0.
Perfect. So I know initial velocity, final velocity, and I know our displacement, or I know x and x naught. Another way to say that. And I'm looking for our acceleration. What equation am I going to use? You remember off the top of your head?
Nope.
V squared is equal to V naught squared plus 2a times x minus x naught, or 2a delta x. Same thing. With me?
Yeah.
Okay, so now we're able to find acceleration real easily. 0 is equal to, we'll just keep V naught squared here. We'll save it till I actually go to plug into the calculator. Plus 2 times 1 is still just 2, so 2 times a. With me?
Yeah.
So that gives me that a, negative a, well, we'll just say a, is equal to, so I move this to the other side and divide it by 2. So it's equal to negative v naught squared over 2.
Yeah.
Uh-oh, acceleration's negative. Is that a problem?
It just cancels out the velocity.
Yeah, it better be negative. We're going from a positive velocity to no velocity. Our acceleration better be negative.
Yeah.
Make sure your signs make sense. Okay, just pointing out that sign makes perfect sense. So now our acceleration is equal to, let's see, our initial velocity was 2.8 squared Oops, forgot to divide by 2. Divided by 2, and we get 3.92 meters per second squared, right?
Okay.
So that's our acceleration due to friction. So what's our force of friction then?
Just divide or multiply that by the mass.
Just multiply that by the mass, perfect. So we take that and we multiply it by 0.45 and we get 1.764, or since this is now our final answer, we now do our rounding to 1.8 newtons.
Isn't it 2?
No, we have two significant figures on everything. I forgot to do it on this one. So we have two significant figures on all our measurements.
Okay.
Don't be confused by the 2 in the formula. That's not a measured number. So we only care about measured numbers when we talk about significant figures.
Okay.
Because it's only our measurements that get off. If a 2 comes up because of some sort of derivation, then that's exactly precisely 2. You can think about that 2.0 with infinite zeros. Anything that comes out of the math is solid. It's only our measurements that can be messed up. Okay, so they didn't want just the magnitude, they also wanted the direction on there, so you could say it's negative, since this is a one-dimensional problem.
At what point does the friction ever turn to 0?
When does friction turn to 0?
Yeah, why doesn't it keep going backwards? Like if it has the force of friction on it, what stops it from going
Friction is only a resistive force. It only resists motion. It doesn't create motion. So as long as that thing's moving, friction pushes back until it stops. The friction's not pushing anymore, because it stops.
So when it stops, there's no friction force.
Correct. Friction is only a resistive force. It resists motion. It can't create motion.
Okay.
It's kind of like air resistance.
Yeah.
Air resistance slows us down as it's moving through. It's a resistive force. That's what we mean by resistive force. It only resists motion, it doesn't create motion. It's trying to make all the motion stop. Okay, so we did that one. Next one. Okay, so in some previous example, they talked about €1 being dropped from the Leaning Tower of Pisa. Euro is just a coin. If the coin falls freely, so that the effects of air resistance are negligible, how does the net force on the coin vary as it falls? So we got the Leaning Tower of Pisa. The coin's dropped right here. What are all the forces acting on it when the coin's right here?
The gravity?
Yeah, so just its weight, mg, right?
Yeah.
What about right here? How do the forces vary as it falls?
It doesn't.
It doesn't.
Okay.
Okay. All right, next. Need some space for this one. Okay, so we have some car that weighs 2.49 times 10 to the 4 newtons. So we know that weight is equal to 2.49 times 10 to the 4 newtons. So some car with that weight is traveling in the positive x direction, and it makes an emergency stop. The x component of the net force acting on it is, so we use F for our net force. The net force in the x direction is equal to negative 1.83 times 10 to the 4 newtons. Oops. times 10 to the 4 newtons. What is its acceleration? Okay, so here's how heavy your car is. You're driving along, I don't know, kid chases a ball, runs out in front of you. You slam on your brakes, and so you create this much net force on you in the x direction, trying to stop you. What's your acceleration? That's what we're trying to figure out. You with me? Okay. So let's start by drawing a free body diagram real quick. So for your car, when you start hitting your brakes, we're drawing the free body diagram for that. With me? So you have your weight pushing down. This is mg, or your weight.
Yeah.
We have the normal force pushing up, because the car's not falling through the road or whatever. And then we have f sub x pushing this way. And these are all the forces acting on you.
What about friction?
You're now slowing down. So friction was resisting your movement, and you're hitting your brakes. So friction was, your car's traveling this way right now. With me? You're pushing your brakes, and there's friction. The net force of those together is pushing you back this way with the net force Fx. So this isn't just from your brakes, this is everything that's going into slowing you down. So friction's accounted for here. Make sense? Okay, so now our problem is to figure out your acceleration, particularly in the x direction, since we're assuming there's none y.
Yeah.
So how are we going to do that?
You just divide the weight by 9.8 to get
The mass. Perfect. So we know that the mass of the car is equal to the weight over g. And that gives us our mass, okay. So now how do I get my acceleration?
Then you take the mass of it and divide that fx by that.
Perfect. So then I know that fx is equal to the acceleration in the x direction times m, which gives me that ax is equal to fx divided by m. Right? So I can just take fx divided by w multiplied by g, and we should be good. But it's exactly what you just said. So we have negative 1.83 times 10 to the 4. So that was fx. And we're going to multiply that by 9.8. And we're going to divide that by 2.49 times 10 to the 4. And it's negative 7.2. Which comes out to negative 7.2. Alright, I just did that. It's roughly negative 7.2 meters per second squared. And we figure out negative 7.20. Oh, so I guess we had three significant figures. I like that. Yeah, we did. But, so yeah, looks like you knew how to do that one.
Yeah.
All right, next example. After your sports car breaks down, you start to push it to the nearest repair shop. While the car is starting to move, how does the force you exert on the car compare to the force the car exerts on you? How do these forces compare when you are pushing the car along at a constant speed? So while the car is starting to move, how does the force exerted on the car by you compare to the force you exert on the car? So if you're pushing on the car's pushing on you, and you get it to move, how do those two forces compare?
Yours has to be greater.
Yours has to be greater to overcome the force of friction or whatever. Okay, so now you're pushing the car along, and you've now got it going 1 meter per second at a constant speed. How does the force you're exerting on the car compare to the car's force on you?
Yours is still greater.
No, now they're the exact same because there's that net force. If there's a net force of 0, the velocity is constant.
Oh.
Make sense? Okay. So, in the first scenario, you have to push a little bit harder to get it going, but once you get it going, it's easier to keep it going with that same speed. So it's harder to get the car going than it is to keep it going.
Yeah.
That make sense? All right, next example. An apple sits at rest atop a table in equilibrium. In equilibrium means no net force acting on it. So its velocity is constant, in this case, constantly 0.
Okay.
So an apple sits on top of a table in equilibrium. What forces act on the apple? So let's draw a free body diagram for the apple really quick. Well, we'll draw a scenario over here. Here's that. We got some apple drawn on top of it. Here's our apple. Free body diagram for the apple. What are all the forces acting on it? There's gravity pulling down, mg, Earth's weight.
Normal.
And then up we have the normal force. And that's it.
Okay.
So, let's have more than just one part. What's the forces acting on the apple? What is the reaction force to each of the forces acting on the apple?
Normal. Weight.
So, yeah, we're going to kind of repeat ourselves for a second here. So, these are all the forces pushing on the apple, but the same way that the apple is pushing down with mg, the table's pushing up with the normal. I don't see any point in restating that. Let's see if they actually have a question worth asking. What are the action-reaction pairs? Okay. Doesn't matter. It's an actual problem to solve. Let's see, next one. A stonemason drags a marble block across the floor by pulling on a rope attached to the block. So we've got some block. There's some rope wrapped around the block. Comes over, and there's a stonemason pulling the block. The block is not necessarily in equilibrium. How are the various forces related? What are the action-reaction pairs? Oh my wow. We really gonna do all this? Okay, let's make the rope longer. Just so we can draw forces on here. Okay, let's count up all the forces. So, on the actual block, what do we have? We'll just draw their free body diagrams underneath it. We have the normal force pushing up. We have its weight pulling down. We have the tension from this rope pulling that way. Inside of the rope, we have tension pulling that way, tension pulling that way.
Yep.
From the man, we have tension pulling that way. We have friction from his feet on the ground pulling this way. That's the friction. There. I don't know why I drew that one down. Just had that as a point. And there's all the forces we have.
Is there any friction on the block?
Oh yeah, there's going to be friction on the block, which will be accounted for in the tension. So let's have friction this way. And maybe if this friction is equal to that tension, then the block's not moving. But if the friction happens to be less than the tension, then he's actually dragging it that way. And so he's able to get enough friction to pull all of it that way. So there would have to be more friction between him and the floor than between the block and the floor for this to work. That's why you probably noticed when you try to pull something heavy, if you can't get your feet set, you can't pull it. You keep sliding. Because you need to get more friction between you and the floor than between the objects in the floor. Otherwise you can't move it. Okay. Was that the last example problem? That was the last example problem. So, yeah, I told you, real easy chapter. So we can spend the rest of the time just going over now any homework questions that you have.
Okay.
And then the next chapter is basically no new material, just harder problems and looking at forces.